Okay, welcome students. Well, back. We're going to cover section 8.2, constant coefficients, homogeneous linear differential equations. Let's get into that, okay? Okay, 8.2, constant coefficient, homogeneous, linear differential equations. Okay, definition. A linear differential equation with constant coefficients can be written in the form of y to the nth derivative plus a1 to the y to the n minus first derivative plus dot 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 plus a n minus 1 y prime plus a n y equals f of x. The homogeneous equation is y to the nth plus a1y to the n minus 1 plus dot 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 plus a n minus 1 y prime plus a n y is equal to 0. The operator form, that d operator we talked about last time, the operator form is P of D, y equals 0, where P of D is equal to D to the N plus A1, D to the N minus 1, plus dot 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 plus A to the N minus 1D plus A to the N, A sub N. And PD, P of D, is the polynomial differential operator. Definition. Okay, P of R equal to R to the nth plus A1 R to the N minus 1 plus dot 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 an minus 1 r plus a sub n is called the auxiliary polynomial and P of R is equal to 0, and P of R equal to 0 is called the auxiliary equation. Okay, so let's do an example. One, right? Differential equation y double prime plus 5y prime minus 7y equal to 0 using its polynomial operator and determine its polynomial, its auxiliary equation. Its auxiliary equation. Okay, so we have y double prime plus 5y prime minus 7y equals 0. Okay, so this y double prime, that's going to be d squared plus 5d minus 7. Okay, times y of y is equal to 0. Okay, so that's going to be my homogeneous equation in terms of my polynomial operator. Okay, now let's find its auxiliary equation. P of R is going to be equal to r squared plus 5r minus 7. Okay, or r squared plus 5r minus 7 is equal to 0. Okay, that's the auxiliary equation. Okay, theorem. Polynomial differential operator. Have linear factors. There, if P of R is equal to r minus r1 to the m1 power times r minus r2 to the m2 power, okay, dot, r minus rk to the m sub k power, okay, where m sub I, the no multiplicity of root r sub I, then P of D okay, just becomes equal to e minus r1 to the m sub 1 times d minus r2 to m sub 2 dot d minus rk to m sub k. Okay, next theorem. We consider the differential equation PD y equals 0. Okay, let R1, R2, dot, 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 to RK be the distinct roots of the auxiliary equation so that P of R equals R minus R1, M1, times R2, sub 2, dot, 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 R minus RK, M sub K, where am I? The M's denote the multiplicity of the root R equals Ri. Okay. We're looking at the roots here, okay, of these auxiliary equations. Okay, number one, if R sub I is a real number, then the function and the functions e to the Ri of x e to the Ri of x, e dot dot x to the m minus 1 of e to the Rix are linearly independent solutions dependent solutions to the differential equation on any interval. I'm just going to abbreviate this. Give me more room. On any interval I. Okay, 2. If okay, R sub j is complex, And so if R ends up being a complex number, okay, if R sub j is complex, say R sub j is equal to a plus or minus bi, then the functions ea to the cosine bx, or eax cosine bx, x eax cosine bx, dot, 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 to x to the mj minus I, minus 1, e to the ax cosine bx, okay, and or e to the ax sine bx, x e to the ax sine bx, dot, 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 x mj minus 1, e to the ax cosine, or so it should be sine, the ax sine bx are linearly independent solutions. Independent solutions to the differential equation on any interval. Okay, number 3. The n real valued solutions to p of dy equals 0 for a general solution to the homogeneous equation maybe I should say form. Okay, the n real valued solutions to PD form a general solution to the homogeneous equation form y of x equals c1 times y1 of x plus c2 times y2 of x plus dot 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 cn plus cn yn of x. Okay, so those 3 things are true. Okay, let's use this to try to solve a second order linear differential equation. Okay, so very, very simple. Let's do example 2 here. Okay, determine the general solution to y double prime minus 2y prime. Oops, not. It's minus y prime minus 2y equals 0. Okay. So okay, our polynomial differential operator PD is going to be equal to d squared minus minus 2. Okay. Okay, so the form of the equation that's going to use my differential operator, the form of the homogeneous equation is going to look like this. Okay, y equals 0. Okay. And so the auxiliary polynomial E of r is going to be r squared minus r minus 2. And the auxiliary equation, r squared minus r minus 0. Okay, so let's solve this. Let's factor this out. We're going to get okay, r minus 2 times r plus 1 is equal to 0. So r is equal to 2 multiplicity 1 equals negative 1 multiplicity 1. Right? Okay. And so go back to the definition here. We have real solutions, right? Okay. So if we had multiplicity of 1, okay, then that multiplicity of 1 corresponds to this guy here, multiplicity of 1. That would just be r minus r1, multiplicity of 1, okay? That just, that would correspond to having no m, okay? Uh, multiplicity 1, meaning that you have there's no multiplicities. Okay, so think of this as x to the, probably should have written it out like this, but the idea here, where my pen go? The idea here is that if I have x, oops, okay, if I have x to the 1 minus 1, okay, and x to the 2 minus 1, okay, then if the multiplicity is 1, then that becomes x to the 0 power. Okay. And so if I have multiplicity 1, then that corresponds to x to the 0 power e to the rix. Okay, and ri is just the particular solution of that I'm working with of r. Mm. So So this is going to correspond to E. Okay, no x in front because it's 1 minus 1. Okay, multiplicity 1 would be 1 minus 1. E to the 2x. Okay, and this guy here corresponds to e to the negative x, because it's just negative 1. If we only have multiplicity 1, then it corresponds to just e to the 2x and e to the negative x. We could say that y sub 1 of x is equal to e to the 2x, and y sub 2 of x is e to the negative x. And so how do I write this as one general solution? Well, it's any linear combination of these two. So y of x equal to c1e to the 2x plus c2e to the negative x. And that would be my general solution to that differential equation. Okay, so it's not that hard of a concept, in practice. We just need to say, hey, if we have this linear differential equation, and with constant coefficients, okay, real coefficients there, that are just constants, then we can use this idea of writing it as a operator, okay, this polynomial differential operator, and then using the auxiliary equation to find my roots. Once I find my roots, I just make those, depending on the multiplicity, I make those my exponents, and then just plug it in to get a general solution. Okay. Okay, let's do one where we actually do have a multiplicity. Okay. And how do we deal with that? Okay, number 3. Solve the differential equation or the initial value problem. Okay, y double prime plus 4y prime plus 4y with y of 0 equaling 1 and y prime of 0 equaling 4. Okay, so let's write this with our differential operator. Our polynomial differential operator. P of d is equal to d squared plus 4d plus 4. Okay. And so this is d squared plus 4d plus 4y is equal to 0. Okay, so that's my differential equation written in polynomial differential operator form. Okay, now I'm going to go PR for my auxiliary equation, r squared plus 4r plus 4 equals 0. Now let's factor this. This is going to become r plus 2 squared equals 0. Okay. And so we have this squared now, which means that r equals -2 is a root with multiplicity 2. Okay, so if we have multiplicity 2, okay, this corresponds to both e to the rx and x e to the rx. Now, why both? Well, it's because x could be 1. okay, we have to account for the fact that x could be 1, but it also could be x. Okay, and so if we have multiplicity, we go up to that, you know, that case. We could have an x, we could not have an x. Okay, so if I had multiplicity 3, then I have to have all three of, I would go up to x squared if I had multiplicity 3. But I'd have to have it represented with each case up to that multiplicity. Both cases need to be represented. Okay, so my general equation is going to be y of x equals c1 e to the negative 2x plus c1x e to the negative 2x. Or sorry, c2x e to the negative 2x. Okay, that's my general solution. Okay. Okay, but we have an initial value problem, so we can find a particular solution. Okay, and clear up those constants. Okay, we know that y evaluated at 0 is equal to 1. So 1 is equal to c1 e to the negative 2 times 0 plus c2 times 0 e to the negative 2 times 0. And so this just becomes 1 is equal to c1. Everything else goes away. Oh, sorry, yeah, c1. Okay, so 1 is equal to c1. Everything else either multiplies by 1 or multiplies by 0. So c1 is equal to 1. Okay. So what about y prime here? Well, y prime, we're just going to take the derivative. That's going to be negative 2c1 e to the negative 2x plus, and now on this one I have to do the product rule. Okay, so this is going to be c2 times the derivative of the first is 1 times e to the negative 2x plus the first times the derivative of the second, that's negative 2 e to the negative 2x. Okay, that's c2. Okay, if I plug in 0, y prime of 0, they're telling me that that's 4. Okay, so again, plug in a 0, that's negative 2c1 e to the negative 2 times 0 plus, I could distribute the c2 here, plus c2 e to the negative 2 times 0. Okay, plus, or minus, I should say, minus 2c2x. Come on, go away. Okay, minus 2c2x e to the negative 2x. Or sorry, e to the negative 2, 0. And this x is a 0. Okay, so this becomes, okay, 4 equals negative 2c1 plus c2. But we know what c1 was. c1 was 1. So this is 4 equals negative 2 times 1 plus c2. Add 2 to both sides. And so 6 is equal to c2. So c2 equals 6. I could write my particular solution, y, of x equaling c1 is just 1. So this is e to the negative 2x plus c2 is 6. So that's going to be 6x e to the negative 2x. I can leave it like that if I want. Or I could factor. Have x is equal to e to the negative 2x plus 6x. And that's my solution. That's my particular solution. Okay. Okay, let's do one last example here. And this is where we get complex roots. Okay, so let's determine the solution, or the general solution, to y double prime plus 6y prime plus 25y is equal to 0. Okay, so let's find our differential operator. Okay, our polynomial differential equation. Okay, polynomial differential operator equation, that's what I should say. Okay, so P of D is equal to, it's kind of a mouthful, E squared plus 6D plus 25 of Y is equal to 0. And so if I take my auxiliary equation, that's R squared plus 6R plus 25 is equal to 0. Okay, and so this is not factored. So I have to use quadratic formula. R equals -6 plus or minus -6 plus or minus the square root of 6 squared minus 4 times 1 times 25 all over 2 times 1. So this is equal to -6 plus or minus the square root. This is going to be 36 minus 100. So that's -64 over 2. So this is -3 plus or minus 8i over 2, which is 4i. So this is -3 plus or minus 4i. Okay, and so I get conjugate pairs. Okay, 2 roots. Okay, I get -3 plus 4i and -3 minus 4i. So I say R1 is -3 plus 4i and R2 is -3 minus 4i. Okay, for this, I'm going to use De Moivre's equation. Okay, or De Moivre's formula. I'm going to say that e to the -3 plus 4i equal to, and x is equal to e to the -3x times e to the 4i times x, okay, which is equal to e to the -3x times the cosine of 4x plus I times the sine of 4x. Okay, that's for the first one. And then for e to the negative 3 minus 4ix, that equals, distribute, e to the negative 3x times e to the minus 4xi. I should have written the other one like that too. And erase it. Maybe not. Or whatever. Okay, which is equal to e to the negative 3x times, okay, cosine 4x minus I sine 4x. Okay. Okay, so any linear combination of these is a solution. Okay, real answers, to obtain real answers, take their sum and difference. Okay. Okay, so any linear combination are a solution. Okay, so to obtain a general solution, sorry, to obtain real answers, real solutions. I guess I just say a real solution. To obtain a real solution, take their sum and difference. Okay, such that y1 would equal to b1 e to the negative 3x times cosine 4x. Okay, cosine 4x, and y2 is equal to c2 e to the negative 3x times the sine of 4x. Okay, so the general solution, okay, so the general solution would be y of x equals c1 e to the negative 3x cosine 4x plus c2 e to the negative 3x sine 4x. Okay, and you could factor out a e to the negative 3x if you wanted. So y to the x equals e to the negative 3x times, it's a negative sign, times c1 cosine 4x plus c2 sine 4x. Okay, and that's it. Let me box my answer. Okay.